All right, so everyone's fascinated by magnets, right? I mean, who isn't? But today we're going way beyond, just your simple fridge magnets and compasses. We're diving deep today into a physics textbook chapter. It's called Magnetism and Matter. And we're going to uncover the mind-bending principles behind this force. You ready? Buckle up. Things are about to get really interesting.
Well, what's so captivating about magnetism is that it's really all about interaction,
Yeah.
like a dance between magnetic fields and the matter that makes up our world. Yeah.
Okay, so let's start with something we can all relate to, like a simple bar magnet. We all know opposites attract, right? North to south. But what's actually going on there?
Think of it this way. A magnet creates this invisible sphere of influence around itself, what we call a magnetic field. And this field isn't just some static aura or anything. It has direction, and it's represented by these things called magnetic field lines.
Right, right. I remember seeing those diagrams back in school, those lines looping out from the North Pole and curving back to the south. But what are those lines actually showing us?
Well, they're showing us the direction that a tiny compass needle would point if you put it at that spot in the field, like a map of the magnetic force,
Hmm.
you know, like revealing how it acts on other magnetic objects.
So these lines are kind of like signposts, guiding other magnets or magnetic materials around.
Exactly. And here's where things get even more fascinating. Unlike electric field lines, which start at positive charges and then end at negative ones, magnetic field lines, they always form closed loops. They have no beginning and they have no end, which leads to this fundamental difference between electricity and magnetism.
Okay, I'm intrigued. So what's this fundamental difference that these closed loops are revealing to us?
It all comes down to the existence of something we call magnetic monopolies. You see, in electricity, we have isolated, positive and negative charges. But in magnetism, we've never, ever found a magnetic charge that just exists on its own, like a north pole without a south, or vice versa.
So you're saying that even if you cut a magnet in half, you'll never isolate a single pole. You'll always end up with two smaller magnets, right?
That's the mystery of the missing magnetic monopoles. And it's one of the things that makes magnetism so unique.
Now, the textbook also draws this interesting parallel between these magnetic field lines and the field that's around something called a solenoid. So what exactly is a solenoid, and why is this comparison so important?
A solenoid is basically a coil of wire that's carrying an electric current. And what's fascinating is that the magnetic field that it produces looks strikingly similar to the field around a bar magnet.
So are they implying that a bar magnet is just like a fancy solenoid in disguise?
Well, it's not quite that simple, but the analogy really helps us understand the underlying mechanism at work here. The textbook suggests that we can think of a bar magnet as like a collection of tiny current loops, electrons whizzing around atoms, all acting like miniature solenoids. And their fields are combining to create the magnet's overall field.
Hold on, are we saying that the magnetism of a bar magnet is due to the movement of electrons within its atoms?
Precisely. This connection between electricity and magnetism is fundamental. Moving charges, they create magnetic fields. It's a key principle that helps explain how magnetism works at the atomic level.
That's incredible. So even though a bar magnet seems like a solid, static object, it's actually buzzing with activity at the microscopic level.
Absolutely. And it's this microscopic activity that generates those macroscopic magnetic fields that we can actually observe and interact with.
Okay, so we've established that magnetic fields really determine how magnets interact with each other. But how does that explain how a compass needle points north?
Okay, so let's visualize a compass needle. Free to rotate, in the Earth's magnetic field. What happens is the needle experiences a torque. It's a twisting force that tries to align it with the Earth's field lines. It's as if the field wants to guide the needle towards a specific direction.
So the needle isn't being pulled towards the North Pole like a metal object to a magnet. It's being rotated to align with the field.
You got it. And this alignment also involves potential energy, just like a ball on a hill wants to roll down to a lower energy state. The compass needle wants to align with the field to minimize its potential energy.
Yeah, so there's this inherent energetic drive for the needle to find its happy place, aligned with the Earth's field lines. That's pretty cool.
It is. Now, this also raises the question, why does an iron nail get pulled towards a magnet? Well, a compass needle just rotates. They're both experiencing the same magnetic field, right?
That's a great point. What's the difference there? Why does one get pulled in while the other just spins around?
It all comes down to the shape of the magnetic field and how it interacts with the object. So the compass needle, being small and pivoting freely, you see, it experiences a relatively uniform field. So it mainly feels that twisting force, the torque. The iron nail, on the other hand, encounters a field that's stronger closer to the magnet. This creates this net force that pulls the nail in. in addition to trying to rotate it, of course.
So the shape of the field itself plays a huge role in how objects behave within it. It's not just about the strength of the magnet.
Precisely. And this brings us back to our elusive magnetic monopoles and a concept called Gauss's law for magnetism.
All right, you've mentioned magnetic monopoles a couple of times now, and it sounds like their absence has some pretty profound implications for how magnetism works. But what exactly is Gauss's law, and how does it relate to all of this?
Gauss's law for magnetism basically says that no matter how you slice it, the total magnetic flux through any closed surface is always zero.
Okay, hold on. You're going to have to explain what magnetic flux is. It sounds a bit intimidating.
It's actually quite intuitive. Imagine magnetic field lines as a sort of flow, like water flowing through a pipe. Magnetic flux is basically a measure of how much of that flow is passing through a given surface.
So if you imagine a magnet enclosed in like a bubble, the number of field lines entering that bubble must equal the number exiting, no matter the shape of the bubble.
Exactly. And that's why Gauss's law for magnetism always equals zero. Because those field lines, they always form closed loops. They have to come out of the surface somewhere if they go in. This contrasts really sharply with electric fields, by the way, where you can have more lines going in or out depending on the enclosed charge.
So Gauss's law is essentially another way of saying that magnetic monopoles just don't exist.
You could put it that way. It really highlights that fundamental difference between electric and magnetic fields.
Now, the textbook also delves into how different materials respond to magnetic fields. And not just iron, but all kinds of stuff. I have to admit, I always thought of magnetism as something that only really applied to magnets and a few metals.
That's a common misconception. Even materials we wouldn't typically think of as magnetic actually interact with magnetic fields in interesting ways. The textbook breaks these interactions down into three main types. We've got diamagnetism, paramagnetism, and of course the familiar ferromagnetism.
All right, let's break those down a bit. Diamagnetism. That sounds kind of familiar, but I couldn't tell you what it means.
Diamagnetic materials are actually slightly repelled by magnetic fields. It's a subtle effect, but it's definitely there. Essentially, when you apply a magnetic field to a diamagnetic substance, it induces these tiny currents within its atoms that oppose the applied field.
So they're kind of like these tiny little rebellious magnets, pushing back against the external field.
In a sense, yes. And here's something that might surprise you. Water is diamagnetic.
Wait, water, like the stuff we drink, so it's slightly repelled by magnets.
It is. It's a great reminder that magnetism is at play everywhere, even in the most commonplace substances.
Okay, that's pretty mind-blowing. So what about paramagnetism? How does that differ from diamagnetism?
Paramagnetic materials have a slightly more cooperative relationship with magnetic fields, you could say. Their atoms possess these tiny permanent magnetic moments, but they're normally oriented randomly.
So they're like a bunch of tiny compass needles all pointing every which way.
A perfect analogy. Now, when you apply an external magnetic field, these little moments, they try to align with the field, resulting in a weak attraction.
So they're trying to get organized, like fall in line with the external field. But I'm guessing it's not quite as strong of an attraction as we see with, ferromagnetic materials like iron.
Exactly. The alignment in paramagnetic materials is much weaker, and it's easily disrupted by thermal energy. The random jiggling of atoms.
So the hotter the material, the harder it is to get those little atomic magnets to line up.
Precisely. Temperature plays a significant role in paramagnetism. Now let's move on to the star of the show, shall we? Yeah. Ferromagnetism. This is where we get those strong, permanent magnets we all know and love.
Okay, bring on the ferromagnetism. This is what I came here for. Iron, nickel, those classic magnetic metals. What makes them so special?
Ferromagnetic materials possess something called magnetic domains. These are microscopic regions within the material, where the atomic moments are already spontaneously aligned, forming these tiny pockets of strong magnetism.
So imagine like a bunch of tiny bar magnets all pointing the same way within each domain. But if they're already aligned, why isn't every piece of iron just like a giant magnet all the time?
Because initially those domains are randomly oriented. It's like this chaotic jumble of microscopic compass needles, all pointing in different directions. But when you apply an external magnetic field,
It's like a drill sergeant yelling, "Attention!" And all those little magnetic domains snap into formation, aligning with the external field.
Exactly. The domains that happen to be aligned with the field, they grow larger, while the others try to rotate to align themselves as well. This creates a strong net magnetization, giving ferromagnetic materials their powerful response to magnetic fields.
So this is how you can magnetize a piece of iron by exposing it to a strong magnet. You're essentially organizing those magnetic domains.
To work together. That makes so much sense. And I'm guessing this also explains the difference between Hard and soft ferromagnetic materials.
You're on a roll.
Huh.
Hard ferromagnetic materials like the alnico alloy mentioned in the textbook are excellent at retaining their magnetization. Once those domains are aligned, they're what we use to make permanent magnets. Soft ferromagnetic materials like pure iron, for example, lose their magnetization much more easily. So a hard ferromagnet is like a stubborn mule, holding on to its magnetic orientation, while a soft ferromagnet is more flexible, willing to switch its alignment depending on the external field.
A very apt analogy. And these differences have immense practical applications. We use hard ferromagnets for things like compass needles, where we need a stable, long-lasting magnetic field. Soft ferromagnets are crucial for applications like electromagnets, where we want to be able to turn the magnetic field on and off.
It's amazing how something as seemingly simple as the arrangement of these tiny domains can have such profound effects on the macroscopic behavior of materials. It's like the quantum world influencing our everyday reality.
It really is amazing, isn't it? How these microscopic interactions can give rise to the magnetic phenomena we experience on a larger scale. And honestly, what we've explored today is just the tip of the iceberg.
I know, right? We started this deep dive hoping to go beyond just the basics of magnets and compasses, and I feel like we've uncovered a whole universe of magnetic complexity.
We certainly have. We've journeyed from that familiar bar magnet, and we've explored the invisible world of magnetic field lines, discovering how they govern the interactions between magnets and all these different materials.
And we wrestled with that enduring mystery of magnetic monopulses and how their absence shapes our understanding of magnetism at a really fundamental level.
And we delved into the, fascinating diversity of magnetic behavior, from the subtle repulsion of diamagnetism to the cooperative alignment of paramagnetism, and the powerful domain-driven magnetism of ferromagnetic materials.
It's almost like magnetism is a whole language, and we've only just begun to learn the alphabet. But even with these basic building blocks, we've gained a deeper appreciation for these invisible forces at play all around us.
Absolutely. So thinking back on everything we've discussed, what stands out to you the most? What's the biggest takeaway for you?
Honestly, for me, it's the realization that magnetism isn't just about attraction and repulsion. It's about this interplay of fields and the movement of charges and this intricate dance of atomic moments within materials. It's a force that's, both subtle and powerful at the same time. And it's shaping our world in ways we often just take completely for granted.
I couldn't agree more. And this deep dive, honestly, has only scratched the surface. The textbook even hints at more exotic types of magnetism, like things like ferromagnetism and antiferromagnetism,
Yeah.
which involve even more complex arrangements of those tiny atomic magnets.
It's like opening one door, only to discover a whole hallway of other doors waiting to be explored. But even with all this complexity, there's still this elegant simplicity to the fundamental principles, like that idea that moving charges create magnetic fields.
That's the beauty of physics, isn't it? Finding those underlying principles that unify seemingly disparate phenomena. And I think that, this deep dive has equipped you with a new lens through which to view the world, one that recognizes those invisible forces at play in everything from a simple compass needle to the matter that makes up our planet.
You're right. I'm already looking at magnets in a whole new light, not just as simple tools, but as windows into the fascinating world of electromagnetism. And I'm definitely going to have to do some more research into those other types of magnetism you mentioned.
That's the spirit. Keep that curiosity burning and never stop exploring the wonders of the universe. Who knows what other mysteries you might unravel?
Thanks for being such an insightful guide on this magnetic journey. And to all our listeners out there, keep those minds curious and never stop questioning the world around you.